This is a lesson on medical uses of radioisotopes and fission and fusion. I wanted to start with a quick recall exercise for you. 3 types of nuclear radiation. Just think what they are. Actually, there are more than 3 types of nuclear radiation. And you'll see when we get to fission below here, another type. There's more than the 4 that we'll talk about today, but so they're alpha, beta, and gamma. Now, we're thinking about medical uses, and we're thinking about, alongside that, of course, the risks involved in the use of radioisotopes around living tissue. So we should consider the factors that come into play with making the radiation dangerous or less dangerous. So what factors do you think might be involved? Pause the video and think about that. One of them, of course, you know already, is the penetrating ability. If the radiation can't enter the body, then it can't do living tissue any harm. So, for example, alpha outside the body is harmless, as long as it's only alpha and as long as it's trying to get through that dead layer of skin on the surface. Inside the body, it is tremendously dangerous because, although it is not very penetrating, it is tremendously ionizing. Now, this term ionizing is a term that you would need to be able to define. It is, in this particular context of radiation, it is the removal of electrons from the atom. Of course, in chemistry, it could be the addition of electrons, but in this particular context, it is the removal of electrons from the atom. So, alongside that consideration, then, is whether this isotope is inside or outside the body. Alpha inside is tremendously dangerous, outside is not. It also depends on which part of the body is being irradiated, because some parts of the body are more susceptible to damage than others. So that's a consideration as well. You need to know the difference between these 2 terms, irradiated and contaminated. Irradiated is being exposed to radiation, and contaminated is having it in or on something. So if I was to drop one of the school sources and a little bit was to fall out, some of the radioactive source inside was to fall out onto the desk would be contaminated. While I am in the vicinity of that contamination, I might well be being irradiated. To put it into another context, soft fruit from supermarkets is irradiated with gamma radiation before it gets to the supermarket, but it is not at all dangerous because it is not contaminated. The irradiation means the gamma radiation has passed through the fruit and as a consequence has killed the bacteria on and in the fruit, so the fruit lasts longer, it doesn't go off as quickly. But there is no radiation, no radioactive source on it or in it, so it is not contaminated. Hopefully that's clear. So irradiation is exposure to the ionizing radiation. Contamination is having in or on something a source of nuclear radiation. So, of course, contamination has a wider meaning than that, but in this context, it's about nuclear radiation. It's about having a source of nuclear radiation in or on something. So it depends on which part of the body is irradiated, and of course, thinking back to earlier work, how long that risk remains a serious consideration depends on the half-life of the source. And that's something you know about quite well. The average time for the activity to fall to half of its current value. Alternatively, the average time for half of the parent atoms to decay, parent nuclei, I should have said, my apologies. So we have to consider the half-life in our medical uses, and the half-life we choose depends on the nature of the application. So, for example, one of the things that we can use radioisotopes for in the body is as a tracer. Now, what we're doing here is we're checking the uptake of certain substances by the body, things the body needs. For example, iodine is used by the thyroid gland to make thyroxine, which is the growth hormone. And we have a radioisotope of iodine, so we can inject that radioisotope into the body, and we can follow its path, its uptake, by the thyroid gland in the neck. So we're pointing our gamma camera at the thyroid in the neck, and we're getting a picture which shows the extent to which the thyroid gland is taking up iodine, because the more iodine is in there, the brighter the picture will be, because there's more gamma radiation coming out. So the function of the thyroid then can be checked using this radioisotope of iodine. We could also attach a radioisotope to the substance and trace its path through the body that way. So one of the big benefits of using radioisotopes is that we can detect very small quantities of it. So we don't have to use very much in order to do what we need to do in terms of tracers. Now, for a tracer, I've already mentioned that we use gamma radiation. We use a gamma source. Now, we need to use gamma because alpha would be no good. It wouldn't come out of the body. It would be absorbed before it left the body, so you wouldn't be able to make any measurements. And we wouldn't want to use beta because whilst beta would come out probably, it would be ionizing on the way out, and the absorption would make it very difficult to tell how much is being taken up, and maybe it would be absorbed by bone, and so we wouldn't see it at some points. So we use gamma because it does come out. It has a high penetration ability, but also because it is weakly ionizing. So as it passes through the body, it does less damage than beta would do, and a lot less damage than alpha would do. So that's why we use gamma, and you need to be able to say that. So do make sure that you are taking notes as you go through this. So that's our first decision made. For any tracer, we're going to use a gamma source. And to be honest, most uses of radioisotopes are gamma. There are exceptions, of course. Smoke detectors use alpha, and paper thickness, metal sheet thickness, like making aluminium foil, these use beta, but most uses you'll find are gamma. Now, the second choice you have to make is the half-life. And in this case, for a tracer, we'd use a half-life of hours. And there's two aspects to the answer to why we do that. One is so the activity remains steady during the measurements. It's no good having a half-life of 3 seconds, for example, because you know the activity when you inject it, but by the time it gets to the thyroid, the activity has fallen dramatically and continues to fall. So you can't really make your measurements because you don't know how much the thyroid is taking up terribly easily. So a half-life of hours, so that the activity falls off rapidly after the procedure which reduces the risk to the patient and those around them. Because once you've been injected with this gamma source, you are a gamma emitter for some time, and you are therefore a hazard to yourself and to anyone that's anywhere near you. So if you were having one of these procedures, you would be told to stay away from pregnant women for a period of time, hours really, but a period of time to avoid any risk to them. So one of the purposes that we use radioisotopes for in medicine is as a medical tracer. One of the other purposes is for radiotherapy. Radiotherapy, as you probably know, is where you are killing cancer using ionizing radiation. Now, you might think, well, ionizing radiation causes cancer, right? So how can you use it to kill cancer? Well, here's the thing. Cancer cells are rapidly dividing cells, and rapidly dividing cells are more susceptible to damage by radiation than non-rapidly dividing cells. So when you have radiotherapy, very often your hair will fall out because your hair cells are rapidly dividing, at least for some of us, not for me, but your hair cells are rapidly dividing, and they are more susceptible to ionizing radiation damage than other cells. So sex cells, sperm cells are particularly susceptible, as are hair cells. So rapidly dividing cells are more easily damaged and killed than non-rapidly dividing cells, and so you can kill cancer cells more easily than you kill healthy cells. So let me show you a little bit about that. So you'll remember from your work on the electromagnetic spectrum that X-rays and gamma rays are up here, and X-rays and gamma rays are really the same thing made in different ways. And although this presentation talks about X-rays, it applies to gamma rays as well. So here we have a patient, and they have been placed very carefully so that the tumour is at the centre of the circle that this source is going to perform. So this source is going to rotate around the patient, and they have been positioned on this bench, which can rise and fall very precisely, so that the tumour is in the centre of the circle. And you would say, well, how do they know that? I'm coming on to that in a minute. So this source will rotate, and it will fire radiation from all directions, gamma radiation from all directions, and the tumour will always be hit, but all the healthy tissue around the tumour, on the way into the tumour, on the way out from the tumour, will get a smaller dose. So you're giving a big dose, relatively, to the most susceptible cells, and a smaller dose to the less susceptible cells. So in that way, you're killing the cancer without killing the healthy tissue. At least not so much. So this is your bundle of cancer cells. It doesn't look like much, but it is a bundle of rapidly dividing cells. The cells are dividing without any control. You know, if you cut yourself, you heal, you form a scab, the skin heals and stops healing. A tumour is where that cell reproduction is out of control. So this is how it works. I've already said all this to you. In terms of X-rays, we're not really talking about X-rays today, but in terms of X-rays, they're produced using a linear accelerator. They fire electrons at a target, and the target atoms emit X-rays. This is how they know. You've probably heard of CT scans, computerized tomography scans, and what they are 3D X-rays. And so by moving the X-ray machine around the patient, taking the pictures, you get this three-dimensional image, and you can tell exactly where the tumour is. You can tell how big it is, and you can tell exactly where it is in the body. Whereas if you had a simple conventional X-ray, you would know that the tumor lies somewhere between here and here, but you wouldn't know where. You wouldn't know how deep the tumor is, and you wouldn't know where in the body it is. Whereas with a 3D X-ray, the CT scan, you can tell exactly where it is, and so you can place this in the center of the circle that we looked at here. And they choose where then to put the patient and how much radiation to fire in. Now you might be saying, well, this is all about X-rays, right? Your gamma radiotherapy wouldn't look any different, really. It's a gamma source that's being rotated around the patient in the same way. And so here you have a computer mock-up of the way the X-rays or gamma rays are being fired into the tumor. So that's how radiotherapy works. You're using gamma because it is the most penetrating and the least ionizing. You're using a rotating source so that you're giving the healthy tissue the smallest possible dose whilst giving the tumor the biggest possible dose at the same time. And so you're killing the tumor because the tumor is more susceptible than the healthy tissue. So that's that then. Now, the summary of that is you use radioisotopes in medicine as tracers or for radiotherapy. You will use a gamma source almost exclusively. There's one example I can think of where alpha is used, but it is gamma pretty much exclusively. If you're using a tracer, the half-life that you would want would be 1 hours so that the activity remains constant during the procedure, but then falls off rapidly afterwards. If you're using it as radiotherapy, well, this is a source you're going to reuse. You're going to have this source time and time again. So you're going to want a half-life of years, maybe. Cobalt-60 would be a typical radioisotope here, gamma emitter. And it is reused. It's not being put into the body. It's an external thing. And so you have a half-life of years there because you'll reuse the source. So that's medical uses, basically. Now, in terms of nuclear fission, there are 2 kinds of nuclear reaction that we're interested in. Nuclear fission is what we do on Earth to make electricity. A nuclear power station uses nuclear fission. And I have a diagram I'm trying to import here, and it's stubbornly refusing to be copied and pasted. There we go. So here we have a uranium nucleus. Now, I've said to you before, it's really important that you talk about nuclei, not atoms. So alpha, beta, and gamma are coming out from unstable nuclei. Uranium-235, there are different isotopes of uranium, and if you come back at A level, we'll talk about uranium enrichment and why we choose 235 as the one to fission. But uranium-235 is a natural neutron emitter. Here's the 4th form of radiation that we haven't talked about yet, and really we won't talk about very much except in this context. So these nuclei are naturally emitting neutrons. The neutrons can be absorbed by another uranium nucleus. That makes it unstable, and so the nucleus splits. This is the parent nucleus. These are the daughter nuclei. Those are the terms we use. And when it splits, energy is released. And 2 more neutrons are released. So here we have 3. Now, 1 neutron splitting 1 nucleus can lead to 3 nuclei being split. And if those 3 nuclei all then have these 3 neutrons coming out, then you go from 1 to 3 to 9 and so on. And every time you have a fission, a splitting, because fission means splitting, every time you have a fission, you release energy. So you have 1 lot of energy, 3 lots of energy, 9 lots of energy. So you can see how this reaction is getting faster and the energy release is rising exponentially. That's dangerous. So this would happen naturally. If you got the enough uranium nuclei together, this would happen naturally. So when we are storing our uranium fuel rods for our nuclear power station, we have to keep them separate so this doesn't happen. And also in the reactor, when we put them all in there to make it happen, we have to control the number of neutrons that can go on to make fission reactions. So this is a diagram you need to be able to draw. 1 neutron colliding with a uranium nucleus, labeled nucleus, splitting, releasing energy, and 2 more neutrons. The more is important, so we've got 3 neutrons here now. They can then go on to repeat this process. So 1 produces 3, produces 9, and so on. So that's an important diagram for you. Now, this is a process that we can do. We're really good at doing this. But there are some real issues with it, as you would know. The nuclear waste produced is quite significant. And it's dangerous. So there are issues with nuclear fission, and we would like not to have those issues. So nuclear fusion would be a great way to go. I'll talk about that in a minute. So if you were to look at a nuclear reactor, you have around the outside this super dense concrete biological shield, which is to absorb any radiation coming out from the reactor here. Inside the reactor, you've got fuel rods, and you've got, those are the long canisters containing the uranium. These go into this enormous block of graphite. Different reactors have different structures, but we'll go with this one. So this graphite, what it does is to slow the neutrons down. So when the neutrons come out of the fuel rod, they are slowed down, they lose energy in the graphite, and what that does is to make them fission the uranium more effectively. Some of the neutrons are too fast to do it effectively, some are too slow. So what we do here is we slow the fast ones down to make them better at fissioning uranium. The control rods made of boron, these are there to absorb the neutrons. So here's how we control the rate of the reaction. These can be raised and lowered through the charge tubes here. These can be raised and lowered to control the reaction. So if you want to stop it, you can drop the control rods into the reactor and all the neutrons get absorbed, the reaction stops. If you want to speed it up, you can lift the control rods out so more neutrons then get through to the fuel rods and cause fission. So that's how we control the reaction, that's how the reaction occurs. How do we get the energy out? Well, all this energy released produces heat, thermal energy. And what you have is a coolant, and the coolants vary. It could be carbon dioxide, it could be sodium, it could be water, but we have coolant circulating through here, which is getting heated up by the fission reactions. The coolant then is used to boil water. So the coolant comes through here, and here we've got water flowing through tubes. The coolant passes over the tubes, and the water in the tubes gets heated, becomes steam, drives turbines out here. More of that when we do electromagnetic induction near the end of year 11. But the process is the nuclear fission releases energy. The energy then is absorbed by the coolant, which boils water, makes steam, drives turbines. So that is basically nuclear fission. And as you know, there are some issues with nuclear fission. You have the nuclear waste, you have the fact that uranium will run out. It's not going to run out anytime soon, but it is not a renewable resource. And that's an important point. Lots of people make that mistake. They think it is renewable. It's not. The uranium will run out, but we're not in any danger just yet in that sense. But the nuclear reactor does produce nuclear waste, and that nuclear waste is more or less a permanent problem. We stick it in mines, disused mines, and holes in the ground generally, and just keep it secure. But we can't, as you know from what we said in earlier lessons about nuclear decay, this is something over which we have no control. We can't speed it up, slow it down, stop it, change it. It just happens. So that spontaneous nature means that we can only just store this stuff, keep it away from people, keep people safe. That's a problem. And of course, if a nuclear reactor has an accident, the consequences can be really, really devastating. You're probably familiar, particularly with recent TV documentaries on Chernobyl. You'll be familiar with the circumstances there to some extent where the reactor blew up and the surrounding area was uninhabitable for a long time. So there are issues here, whereas nuclear fusion, which is what stars do to produce the energy they produce, nuclear fusion doesn't have these problems. It doesn't produce lots of nuclear waste. It produces some low-level, short-lived nuclear waste. It releases a lot more energy per kilogram of fuel. So it sounds great, but unfortunately it doesn't work terribly well. And so whilst it's a great idea, we've been spending the last 40 years or so trying to make it work. We're getting better, but we're not there yet. So nuclear fusion is the taking of small light nuclei, hydrogen, for example, and combining them into a larger, heavier nucleus, helium, and in the process, energy is released. Nuclear fission is taking a large, heavy nucleus, like uranium, and splitting it into smaller, lighter nuclei, like barium and krypton are typical products here, and energy is released. So there you have fission and how we use it, fusion and how we'd like to use it. The problem at the moment is that we are putting in as much energy to make the reaction happen as we are getting out of the reaction, because in order to make the reaction happen, the principal way we do it is to heat the whole thing up to 100 million degrees centigrade. That's very hot, and the heating of the fuel and the containing of that very hot fuel, keeping it where you want it, takes a lot of energy. And the energy that's released by the fusion then is about the same as the energy it takes to make it happen. We need about 7 times as much come out of the reaction as we're putting in to make it happen, to make it viable.